Today, we start Module 4, Divide and Conquer approach. Part A, Introduction to Divide and Conquer and Insertion Sort. The first video, A.1, start with Insertion Sort. Actually, at this point, we have learned this Divide and Conquer approach already through several examples. So later, when we talk about the details, I can recall some of the examples. All right, first, this name, based on our textbook, it calls decrease and conquer. So it tried to narrow down a special case or try to provide more precise description on divide and conquer, because how to divide, there are many different ways. Here, it just take one special angle using the decrease way. All right. Its meaning is like this. Under a similar situation, so you try to make your problem, try to formulate your problem under similar situation, but for different problem size. Different problem size. But the format of the problem exactly the same. So when you have that situation, so then you try to explore the relationship between a solution of a given instance. So that's the current problem size. So when you work on problem with the given size, you can call it current instance. But when you work on it, you can consider its relationship with similar problem, but the problem size is smaller. So you compare those two instances, also another instance, two instances, similar problem, but for two different instances. The reason they are two different instances because they have different problem sizes. So that's the situation. All right. Now the question, how to divide? Here, there are three cases. All right, so we try to characterize. Typically, we can see these three classes. The first one, decrease by a constant. Most of the time, that constant is 1, because that's the most popular size reduction. Reduce the problem size exactly by 1. That's the most popular problem size reduction. There are smaller other cases, so you can reduce by more than 1 size. That's possible, but the percentage much smaller. All right, so that's the decrease by a constant. But there is another special case, so that's the decrease by a constant factor. So this time is not the minus subtraction situation, division, divided by a constant number. You suppose your problem size is n, you reduce the problem size by a constant, 2, 3, 4, 5. So things like that. That's another special class. We have example. We learn example. So remember that counting binary digits problem. If you recall, counting binary digits problem. So that one, so I just write it out. Counting binary digits problem. That belongs to this category because binary when we do binary divided by 2, so that constant factor is 2. The problem size by 2. Yeah. Then variable size decrease. You cannot have a fixed size reduction. Every time the size reduction could be different. Yeah. For this case, we also have a very good example. Very good example. GCD, greatest common divisor. GCD problem, greatest common divisor. That belongs to this category. So you can see, we have some very nice examples. So before we, in this module 2, before we learn more examples, we have already learned several nice examples that belong to this part. And this module is a big module, pretty big module. So we will have 5 parts, A, B, C, D, E, 5 parts. So you can see the importance of this module. Other than we covered in our previous 3 modules, we have a few, 5 more parts to cover. Anyway. All right, so you just know the importance of this topic. But here I want to make some comments. I remember I mentioned this, terminology before. The author of our textbook, it calls this decrease and conquer. Decrease, especially this part. So usually people do not call it this way. This is, the author's opinion. So other people may not choose this way to call it. So most people, 90-something%, they just still call the traditional divide and conquer, because it is more popular and most people can understand the meaning immediately. Because if you call decrease and conquer, people need to ask you for the details. What do you really mean? You need to explain a lot, right? But if you say divide and conquer, not many people need you to explain. So that's the reason. So I prefer this terminology, traditional divide and conquer. Okay. All right. Just let you know. All right. Then, before we move to the next topic, because this video, we do simple introduction to divide and conquer. So I want to explain another important thing for divide and conquer. So that is the components. Components of divide and conquer solution. So when we work on divide and conquer, we need to have these 3 components. Okay, during the problem solving. When I do analysis to find a solution, so I will use these 3 components. Okay, so what are these 3 components? Divide and conquer, the first thing you need to do, divide step, right? So very natural. So divide step. Divide. So that's the first component. Okay, so you need to do some work. Okay, how to divide, first component. Second component, conquer. That's very natural. Conquer, divide and conquer. Okay, all right. Conquer what? Conquer what? What? When you do divide, you split original problem to smaller problems, right? Smaller problems. So you may have several smaller problems. Okay? After that, when you do conquer, you conquer those smaller problems. So we call subproblems. Subproblems. So that's the conquer step component. Then after that, you have the last component. You have some amount of work you need to do. The last one, combine the results. You need to combine the results. Combine. Yeah, because after you get all the solutions of your subproblem, you need to combine all the results. These are the three components. So very basic, fundamental. But in our future discussion, we will look at each step. For each step, what should we do? Sometimes we make the divide step very easy, but you have trade-off. You cannot make every step very easy. That's impossible. If you make the divide step very easy, then as a result, usually your combined step could be very hard. Okay? All right. If you make the combined step very easy, then the trade-off principle, then your divide step could be hard. But why not conquer step? Because conquer step usually we do not need to do anything special. The conquer step, we just do recursion. Recursion. Okay? Recursion. Recursive call, right? Yeah. Similar situation. So you split, you get a smaller problem, but a similar problems. So you can call the recursive function. So the conquer step, we use recursion. So that's why it is pretty easy. Yeah. We do not need to do anything special. Conquer, recursion. Yeah. But these two steps or components, we need to spend most of our time. All right? Yeah. So this kind of basic information to give you here, and later in our discussion, we will look at the details of all, typically first and the last components. Yeah. All right, so that's the basic information about divide and conquer. Yeah. Before we move to problem solving, our next slide, I will give you a new problem. Yeah. But before we go there, we also want to consider another small problem. Yeah. So that's the recursive or non-recursive options when we solve a problem. So we have these two options. Because when we do divide and conquer, typically we will get a recurrence relation. Okay? Yeah. Because divide, conquer, combine, right? So typically you will get a recurrence relation. Recurrence relation. But when you have a recurrence relation, it is very natural that people like to use the recursive way to implement the algorithm. Now, people tend to do that. Follow the natural format of the your formulation of the solution. Yeah. But it may not be a good way to solve it. It may not be a good way to solve it. Sometimes you may like to avoid it. So that's why we look at this topic, recursive or non-recursive. This topic. All right? Yeah. All right. So here we already have that recurrence relation. Yeah. Yeah. So naturally, people will work on the recursive implementation. But you need to be aware of the problem, potential problem it may have. Yeah. All right. So The problem is, I remember I mentioned once before in one of the videos before. Yeah, I couldn't remember which one, but I remember I mentioned this issue before. That's the storage space. Storage space issue, right? How much space do you need to solve your problem? And if you solve recursively, look at the storage space you used. Okay? The storage space you used because, remember, inside the programming language, high-level programming language, to implement recursive function call, usually it uses stacks. Okay? Yeah. So then stacks use a lot of memory, right? Memory space to implement that stack data structure. Yeah. Sometimes the stack could be very deep. When the stack is very deep, then a lot of memory space is used. So that is not quite efficient. Yeah. That kind of situation, if you are a good programmer, you should try your best to avoid it. Try your best. Yeah. Sometimes you may not be able to avoid it. That's true. Sometimes you cannot avoid it. Think about our problem, the Tower of Hanoi problem. Right? The Tower of Hanoi problem. That one, that's a good example. That solution, I don't believe anyone can avoid recursive implementation. Yeah, I cannot. Yeah, it's very hard to find a non-recursive way to implement it. Yeah, so that's why I said try your best to avoid it. Yeah, but if you cannot, yeah, so that's okay. Yeah, yeah, but if you can, yeah, try to avoid it. Yeah, all right. Yeah, so here you want to save storage space. Yeah, all right. The method, typically the method used. How do you change recursive implementation to non-recursive, iterative? Yeah, more specifically, you use the iterative way to implement. Yeah, bottom-up approach. You start with a solution for base cases, right? Recursion, you will have base cases. Yeah, 1 or 2, Fibonacci, 2 base cases. So usually you have some base cases you can start with. Yeah. So from there, then you, based on the recurrence relation, you call it iteratively. Yeah. Yeah. In that kind of implementation, you do not need to use a deep stack. Because iteratively, no recursive call, you do not use that stack implementation. Okay, so you use variables. Yeah. Every time you use variables, temporary variables, when you have new values, you override old values. So you can reuse same set of variables again and again to save a lot of storage space. So that's the typical idea. Okay, yeah. So with that kind of understanding, yeah, then in the future, so when you solve typical computing problems, most of the time you may have the divide and conquer situation. Yeah, because this is the most popular situation you may have in the real world computing problems. So you have that. Yeah. So then you have this in your mind. Right? Try to save storage space, but there is a limit. Okay? There is some limit. Yeah. So you cannot avoid all the recursions. So that's impossible. Yeah. So with this kind of understanding, yeah, you should be fine. Yeah. You try your best. You can get the best solutions with your effort. Yeah. All right. Yeah. So that's the introduction part. Yeah. After that, let's start new problem. So actually, it is an old problem because the sorting problem, it is old. We did several times, right? Selection sort, bubble sort, right? So we did 2 old algorithms. This time, we will learn our 3rd sorting algorithm, insertion sort. So let's look at the problem. The same problem, number 4, we revisited another time. Yeah. So we're familiar with this problem. So we do not need to explain this problem another time. We just go to our solution directly. Yeah. First, strategy. Yeah. So we always talk about strategy first, yeah, then implementation. Yeah. For the strategy of this problem, it's an old one. Yeah. So we use this strategy many, many times. Yeah. Start with a simple case. Base case, the simplest possible case or instance. Yeah. So the formal name, yeah, it calls instance. Yeah. It's okay. Yeah. So then we grow the size, data size gradually. We increase the data size. Every time we increase by 1. Okay? So incremental way. Just the opposite of the decremental way, right? Yeah. Decrease and conquer. Decrease. Yeah. Decrease by a constant. Decremental. But incremental, just opposite. Yeah. So we treat the same. Yeah. Incremental. Yeah. All right. So every time increase the problem size just by 1. Yeah. Yeah. So this is also a popular way to solve a problem. Yeah. All right. But the question is how to connect 2 other JSON cases or 2 other JSON instances. Yeah. If we use the terminology, yeah, of the textbook, instances. Yeah. All right. That's the key. Yeah. That's the key. Connect 2 instances. Yeah. All right. Other JSON instances. Yeah. Let's do the work here. Okay. When we do this work, so let's use some diagram, draw some diagram, because we need some visualization. Yeah. We need to use our intuition to understand the problem. Yeah. When we start with the smallest array. If it's not empty, smallest non-empty array. So here, this array just has 1 element. Yeah. 1 array. Yeah. Yeah. Then we want to add a new element into this array. This is a A1 new element. But after we add into the current array here, and we want to make the whole thing sorted. Yeah. 2 elements. Now we have a 2-element array. This 2-element array, we want to make it sorted by comparisons. Here you can see we need 1 comparison. We can get it sorted. Okay? Yeah, that's simple. Yeah. All right. Then we gradually increase the data size. Next step, our starting point, we already have an array with 2 elements. That's our starting point. But now we look at a 3rd new element. And we want to make this 3rd element join the current 2 elements in the array. But at the end, we want them sorted. we want all the 3 elements sorted. That's the visualization. Visualize the way to understand this problem. Okay, then keep going. Yeah, we keep doing this. Yeah, so this is our, description. So what we are doing right now, it's just this. Yeah. Add a new element to a current sorted array. We assume the current array already sorted. Yeah. But after the new element joins the current array, it is not sorted automatically. You need to do some work to make it sorted. There is some work to do to make it sorted. What is that work? That's our next discussion topic. What is that work we need? Right? Yeah. The general instance. Now we look at the general instance. Okay? So we have a sorted array that contains k elements. Now there is a new element, ak. We want to make it join the current array and make the new array sorted. Yeah. So now we want to look at our visualization. What conclusion can we get, right? What conclusion can we get from this diagram? So we rely on our intuition. Intuition is important. In problem solving, intuition is really important. You need to have imagination. Intuition, imagination, right? Yeah. So here, our observation for this kind of whole procedure. So we try to find some special rule, and we try to summarize what we typically do each step. Yeah. So we can understand in this way. Insert an element. Insert. So here, what we are doing is insertion. Insert. Yeah. Insert. Yeah. This is important view of the problem. Important view. Okay. This is our way of understanding. Understanding is important. How do you understand? Here, we use the insertion view to understand this problem. Okay? Here you can compare our solutions. Selection sort, we do not use the insertion view in selection sort, right? Bubble sort, we do not use the insertion view in bubble sort, right? So here you can see when we solve the same problem, sorting problem, we take different views. Selection sort, what view do we take? Selection sort, what view do we take? Okay? Minimum element in the current subarray, right? We put it in place. That in place view, okay? Yeah. So I want to summarize. Here, let me summarize, okay? Yeah. Selection sort. Selection sort, what view do we take? Okay? In place view. Okay? Every time we make one element in place. So in place view. Okay? All right. What is the bubble sort? What is the view of bubble sort? What view do we take in bubble sort? Inversion, right? Remember the concept inversion. Every time we use swap two adjacent elements that are out of order, we reduce the number of inversions. So the view we use, we can call inversion view. Inversion view. Bubble sort. We use the inversion view to solve. All right? So now insertion sort. insertion sort. This time we take another special view to solve it. So that's the insertion view. So you can see, yeah. Next time when we move to other sorting algorithms, we will change our views many, many times. Okay? All right. Yeah, so yeah. Then, so this time we know this insertion operation is critical. Very important. So our next video, we need to study the insertion operation. The details of insertion operation. All right, so that's it. Yeah. So we finish our video 8.1.